It's September 1939. Britain is at war. Out in the Atlantic, German U-boats are quietly sinking Allied ships faster than they can be built. Every ship lost means more lives gone. More families waiting for news that never comes. When you picture World War II, you probably think of tanks, planes and soldiers. But behind the scenes there was another kind of weapon. Information. German commanders coordinate their attacks using messages encrypted by a supposedly unbreakable machine. Enigma. The British government assembles an unlikely team at a secret facility called Bletchley Park. Mathematicians, chess champions, linguists and crossword experts. Among them is a shy, brilliant young Cambridge mathematician named Alan Turing. He doesn't just break codes, he starts to turn thinking itself into something a machine can help with. He begins to ask, what if reasoning could be turned into steps? Steps a machine could follow. This is how World War II quietly gave birth to the computer age we live in today. Turing's bomb machines don't just calculate, they reason. They eliminate impossible combinations. They use earlier results to guide new searches. They make logical deductions at inhuman speed. Each machine was essentially a mechanical brain, working through possibilities far faster than any human team. The bombs worked. Allied shipping losses dropped dramatically. Some historians estimate Turing's work shortened the war by 2 years, saving millions of lives. But Turing had proven something even more profound. Complex reasoning could be mechanised. By 1943, the Germans had developed an even more sophisticated cipher machine, the Lorenz cipher, used for Hitler's highest level communications. Breaking it required something beyond the bomb. It required the world's first programmable digital electronic computer, Colossus. Built by engineer Tommy Flowers, Colossus used 1,500 vacuum tubes and could process about 5,000 characters per second. It could be reprogrammed by plugging cables and setting switches. Essentially, it could run different algorithms. 10 colossi were built during the war. They cracked top-level German communications, giving the Allies crucial intelligence for D-Day and beyond. But here's the tragedy. Colossus was classified for decades. Most of the machines were destroyed after the war. The men and women who built the world's first digital computer went home, got ordinary jobs, raised families and couldn't even tell their loved ones what they'd done. Imagine carrying that secret for the rest of your life. The computer age had begun, but it had begun in secret. Across the Atlantic, the US Army faced a different problem. They needed to calculate artillery firing tables. Doing this by hand took months. In 1945, the ENIAC came online. ENIAC stood for Electronic Numerical Integrator and Computer. It filled an entire room, weighed 30 tonnes and used over 17,000 vacuum tubes. And it could perform about 5,000 calculations per second, thousands of times faster than any human. The ENIAC was programmed primarily by women. 6 young women who developed early programming techniques that we still use in spirit today. Their names were Jean Jennings, Marilyn Westcott, Ruth Lichterman, Betty Snyder, Frances Belas and Kay McNulty. You don't usually hear those names in school, but they were doing what we now call software engineering. They had to physically rewire the machine for each new calculation, pulling cables, setting switches, while we now just click run on the laptop. The war ended and the atomic age began. Scattered across America and Britain were these massive, powerful calculating machines and the brilliant people who built them. The obvious question now was, what else could these machines do? John von Neumann was, by many accounts, the smartest person in almost any room he walked into. He'd worked on the atomic bomb, game theory, quantum mechanics, and now he turned his attention to computers. In 1945, von Neumann described what we now call von Neumann architecture, a computer where programs and data are stored in the same memory, allowing the machine to modify its own instructions. Now this sounds technical, but it's revolutionary. It meant computers could store their programs instead of being physically rewired and even modify their own code, essentially adjust their own behaviour. Every computer you've ever used uses von Neumann architecture. Your phone, your laptop, even supercomputers. But von Neumann saw even further. He wrote about computers that might self-replicate, evolve their own programs and eventually surpass human intelligence. He was sketching out ideas that sound a lot like artificial intelligence. In 1945, Norbert Wiener had spent the war developing automated anti-aircraft guns that could predict where enemy planes would be and automatically adjust the gun's aim. This required something amazing, machines that could sense, predict and adapt, just like living organisms. In 1948, Wiener published Cybernetics, or Control and Communication in the Animal and the Machine. Cybernetics showed that the same principles govern both living beings and machines. Input sensing, processing deciding, output acting, and feedback learning from what happened. Now if that sounds familiar, it's because this is how you learn too. You try something, see what happens, adjust and try again. Wiener argued there was no fundamental difference between biological and artificial intelligence. Both followed the same logic of information control and adaptation. Cybernetics became phenomenally influential, inspiring robotics, artificial neural networks, cognitive science and systems theory. Wiener had given researchers a framework for building intelligent machines. Claude Shannon was already famous for applying Boolean logic to telephone circuits, essentially founding digital circuit design. But in 1948 he published something equally revolutionary, information theory. Shannon showed that all information, text, sound, images, even ideas, could be encoded as sequences of bits, ones and zeros, and transmitted, stored and processed mathematically. The messy richness of human communication, music, words, pictures, could all be turned into long strings of ones and zeros. Information wasn't mysterious anymore. It was measurable, quantifiable, computable. Then in 1950, Shannon published a paper called Programming a Computer for Playing Chess. He described exactly how a computer could evaluate possible moves, search ahead multiple turns, and choose the best strategy. Shannon wasn't just describing a chess program, he was describing machine decision making. He even built a mechanical mouse called a Theseus that could navigate a maze, remember the path and solve it faster the second time. Watching this little artificial mouse remember the maze was like seeing a toy come to life. It wasn't just following a script, it was changing based on experience. It was learning from experience. In October 1950, Alan Turing published a paper in the philosophy journal Mind titled Computing Machinery and Intelligence. It opens with a direct challenge. I propose to consider the question, can machines think? If that question sounds familiar, it's because we're still asking it today, every time a new AI model comes out and people say, okay, but is it really thinking? Turing immediately recognises the problem. Thinking is too vague, too philosophical, so he proposes something brilliant. A test. Imagine you're a judge, you sit at a terminal having typed conversations with two hidden entities. One is human, one is a machine. You can ask anything you like, but you don't know which is which. If you as a judge cannot reliably tell them apart, then the machine has passed the test. Turing argued that if a machine could convincingly imitate human intelligence, then the philosophical question of whether it really thinks becomes less important. Intelligence, he suggested, is as intelligence does. The paper sparked furious debate. Can machines truly think or just simulate thinking? Could a machine have consciousness? What does it even mean to be intelligent? Now, these debates didn't stay in philosophy journals. They're alive every time you interact with ChatGPT, Claude or Gemini. But Turing did something crucial. He made machine intelligence testable. Turing also made predictions. By the year 2000, he believed machines with 100 megabytes of storage could fool judges 30% of the time. He was both optimistic and pessimistic. We've built far more capable machines than he imagined, but whether they've truly passed the Turing test is still controversial. Turing's real legacy, though, wasn't the test itself, it was changing the question from can machines think to how do we build machines that think. While the war still raged, a neuropsychiatrist named Warren McCulloch and a young logician named Walter Pitts published a paper with a long title, A Logical Calculus of the Ideas Immanent in Nervous Activity. They showed that neurons, the cells in your brain, could be modelled as simple logical devices. Each neuron receives multiple inputs, fires if the total exceeds a threshold, and sends its output to other neurons. They proved that networks of these artificial neurons could compute any logical function. And this was staggering. It suggested that a biological brain was in principle computable. McCulloch and Pitts had created the first artificial neural network model, the ancestor of today's deep learning systems. But McCulloch and Pitts' neurons couldn't learn. Enter Donald Hebb, a Canadian psychologist, who asked a simple but powerful question: how do real brains learn new things? Hebb proposed a rule: when neurons repeatedly fire together, their connection strengthens. This is now called Hebbian learning. It's one of the core ideas behind how artificial neural networks learn. Want to teach a network to recognise a cat? Show it thousands of cat images. Neurons that consistently activate together when seeing cats strengthen their connections, eventually forming something like a cat detector. If you've ever wondered how modern image recognition works, this is a basic idea, refined, scaled up and run on massive hardware. Hebb's insight was crucial. Intelligence isn't just architecture, it's learned patterns. At IBM, a quiet, persistent researcher named Arthur Samuel had a radical idea. Instead of programming a computer with fixed rules for playing checkers, what if the computer taught itself by playing thousands and thousands of games? By 1952, Samuel's checkers program could play against itself repeatedly, learn which ball positions were good or bad, and improve its strategy over time. By 1955, his program could beat amateur players. By the 1960s, it was defeating checkers masters. Samuel coined the term machine learning. He wrote, programming computers to learn from experience should eventually eliminate the need for much detailed programming. He was describing the core idea of modern AI, computers learning from data, in 1959. All these threads, computing, learning, neural networks, logic and cybernetics, were swirling through the research labs across America and Britain, but they weren't yet a single field. There wasn't a name for what all these people were collectively trying to do. But that was about to change. In August 1955, 4 researchers submitted a proposal to the Rockefeller Foundation: John McCarthy, Marvin Minsky, Nathaniel Rochester and Claude Shannon. They wanted to organise a summer workshop where researchers could work together on a revolutionary topic. The proposal read, "We propose that a 2-month, 10-man study of artificial intelligence be carried out during the summer of 1956 at Dartmouth College. The study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it." This was the first time the term artificial intelligence appeared in print. It's the summer of 1956. A small group of researchers arrive at Dartmouth College in New Hampshire. It's hot, the campus is quiet, and in borrowed rooms a handful of people are trying to figure out how to build thinking machines. They debated, can machines be creative? How should machines represent knowledge? What's the best approach? Logic, learning, or something else? Could machines eventually become conscious? But the conference wasn't just talk. Alan Newell and Herbert Simon arrived with something extraordinary, a program called the Logic Theorist. It could prove mathematical theorems from Russell and Whitehead's Principia Mathematica. The Logic Theorist didn't just follow a fixed script, it searched through possible proofs, discovering solutions its creators hadn't explicitly programmed. On one theorem it even found a more elegant proof than Russell's original. For the people in that room, watching a machine do this was unsettling and exhilarating at the same time. It felt like a new kind of mind had just walked into mathematics. A machine had done creative intellectual work. The Dartmouth conference didn't solve artificial intelligence, but it did something crucial. It created a community. Before Dartmouth, researchers were scattered across disciplines: mathematics, engineering, psychology, linguistics. After Dartmouth, they were AI researchers. They had a shared name for their work, a common vision, and proof that intelligent programs were possible. And they had dangerous amounts of optimism. Simon and Newell predicted in 1958 that, within 10 years, a digital computer would be the world's chess champion. They were off by about 40 years. But the age of artificial intelligence had officially begun. The next decades would bring triumph and frustration, breakthroughs and dead ends, wild hype and bitter disappointment. And that's what we'll explore in the next episodes. If you've enjoyed this little time travel through the early days of AI, please hit the like button. It really helps this series reach more people who are curious about the AI story. And if you hit the subscribe button, you'll get notified when the next episode is available to watch. Subscribing won't cost you anything, but it does tell me that you'd like to see more of this series. Thank you for watching, and let me know in the comments which part of this early AI story surprised you the most. I'm Ian, and this is the AI Story. Hope to see you next time.